I wanted to try a slightly different buffer calculation, and this is actually the calculations that show up on the worksheet that we have called buffer calculations. Now, during a buffer, what we know is that we have some weak acid and we have some weak base, and those are mixed together. This makes it into a nice buffer solution because we have the acid here, which can donate any H's that are taken away, and we have our conjugate base, which can mop up any excess H's that are added, H pluses that are added. So that'll keep the pH pretty constant. Now right now we're sort of showing where the acid and our conjugate base are equal, and that would be right about here on our curve, about halfway to the equivalence point. So here's the equivalence point, we can see, because here's the inflection point, and that's at 25, so at about 12.5. Here we have our perfect buffer where the acid and the conjugate base are equal, and so the pH equals the pKa of our acid. Now, what we want to do on this calculation is to figure out the number here, and then we also want to say, well, let's mess up our buffer just a little bit by putting in some acid. Now, if we put in some strong hydrochloric acid, that is going to protonate our weak base and turn it into our acid. So we're going to change a little bit of our base into our acid, and that's going to move us a little bit this way. So we're going to have another point, just slightly different. We start off with several equations, and I show all three equations because it gets confusing because we're going back and forth and back and forth. So we would say here at the very beginning, all we have is a solution of our acid. So we would use our acid equilibrium and do an icebox to figure out the pH at that point. Then as we add our base, we're going to be using the second equation. So we can go from our acid to neutralized. Then when we get completely neutralized, this would be right about here, halfway up this inflection point, where the slope stops going up and up and starts going down and down. So that'd be our equivalence point. And at the equivalence point here, if we wanted to calculate that pH, we would be using this third equation. And that's not part of what we're doing. What we're doing right now is looking at this buffer region. And so while we're in the buffer region, we are still using our acid equation originally. So we use the acid equation all the way up until we get to the inflection point, and we are changing our acid into our base by using the neutralization equation. So these top two equations are part of what we're doing today. Problem 1 is a buffer solution is prepared by adding 0.1 liters of 2 molar acetic acid to 0.1 liters of 1.0 molar sodium hydroxide. So we've seen this before. Here we have our weak acid, and we're going to put in half as much of our strong base. That's going to change some of our acid into our base, and we will get a buffer. So first off, what we want to do is just to do an icebox. That's not really the equilibrium, it's just our neutralization to figure out what kind of numbers do we have when we make our buffer. If we have a 0.1 liter of 2 molar acetic acid, then we're going to figure out how many moles of acetic acid and divide by the total volume. Now the total volume, we can see that right now because we have 0.1 liters of the acid and we have 0.1 liters of our base. So our total volume here is 0.2 liters. So we'll save that for a few moments now. To get our moles, we know that volume times molarity will give us our moles. So for our acid, we have 0.1 liters times 2 molar, and I'm reducing my significant figures just so I have some room. And what I'm going to get from this is 0.2 moles of my acetic acid. I'm going to call that HAC because I don't have very much room. To get my concentration that I want to put up in my top box here, then I'll take that number divided by my volume, and I can see 0.2 divided by 0.2, then that's going to be a 1.0 molar solution. Now the next thing I want to do is to get my base. Now my base, I can see I have same volume. I have half as much, half the concentration, 1 molar instead of 2 molar. So I can just see what's going to happen is I'm going to have 0.1 liters times 1 molar. So that's going to give me 0.1 mole. And when I take 0.1 mole divided by 0.2 liters, I'm going to have 0.50 molar. And to start with, I have no water, and to start with, I have no acetate, and I don't really care about the water anyway because it's a liquid. Well, you can see what's going to happen is when I mix my acid and my base, all of my base is going to be used up. So I know that's minus 0.5. That's going to make this guy plus 0.5. And this one over here will be minus 0.5. Now I don't really need to do an icebox to get all these numbers, but if I do it this way, it helps me keep everything straight and I don't get confused later on. So after I've added this much base to my acid, then you can see that I have equal concentrations of my acid and my base. So just to review, I am using the acid equilibrium is what I'm going to use in order to calculate my buffer concentrations. But right now, I'm just using the acid-base reaction where I'm going to take some of my acid and I add some hydroxides and turn it into base. Now these equations are from another problem, but you can see that I keep using those same kind of equations over and over. Now, second part of this, I'm still on part A, but second part of this is I start off with my two concentrations, and again I don't really want to care about my water because it's a liquid, and I'm starting off with 0 H pluses. And we'll say let's let this come to equilibrium and see what kind of numbers we get. I wrote in my Ka, and we know for acetic acid it's 1.8 times 10 to the minus 5, and we're to a standard icebox now. So x of this is going to go away. I'm going to form x. I'm going to form x. And the only big difference between this and other equations we've done in the past is I'm starting off with some of my acid and some of my conjugate base. So since I have both of those, it slightly changes my icebox. The other icebox problems we've done before, both of my products started off as 0. Now, so this will be 0.5 minus x, 0.5 plus x. Now I'm actually going to make my equation a little bit more complicated because I'm going to have some extra x's in here. However, we can go ahead and make the assumption that x is much smaller than 0.5. And if I have more room, I would write out my statement. Say x is much smaller than 0.5, therefore 0.5 minus x is approximately 0.5, and 0.5 plus x is approximately 0.5. We can do this because our initial concentration, 0.5, is quite a bit larger. It's well times over 1,000 times larger than our Ka, which is 1.8 times 10 to the minus 5. This is 10 to the minus 1, 10 to the minus 5. Also, because I have some of my conjugate base in here, that's actually going to drive my reaction a little bit back, making x even smaller than it would be in a normal icebox problem. So x is very, very small, totally ignorable. So I have x times 0.5 divided by 0.5 equals 1.8 times 10 to the negative 5. Because those two are equal, they cancel, and we realize we are right here in the middle of our buffer region where we have equal concentrations of the acid and its conjugate base. So in this case, my H plus concentration equals the Ka, which is 1.8 times 10 to the minus 5. Now, just for our own information, then the pH of this solution would be the negative log of 1.8 times 10 to the minus 5, which is 4.74. Now, the problem doesn't ask for that, but if we were doing a titration curve, we would need that. Now, part B, this is where we take a little bit of our acid, some hydrochloric acid, which is not part of our equilibrium, and we're just going to throw it in with our buffer. Now, here's our buffer. We know that we started with 0.5 molar of each of the two concentrations that we had before. Our buffer is 0.5 molar of the weak acid, 0.5 molar of the weak base. But now, if we're going to add 0.01 liters of some hydrochloric acid, that is going to change our total volume. So, if we have 0.2 liters of the buffer, and we add 0.01 liters of some acid, then our new volume is going to be 0.21 liters. And because of that new volume, that's going to mess up all of our calculations a little bit. So our base and our acid that we started with are going to be slightly different. We're going to say the base is 0.2 liters and we're getting this here from the 0.2 liters of our buffer times the concentration we had before, which was 0.50 molar. We're getting that from our buffer, and that gives us 0.1 moles of our base and our acid. Both of those numbers are in the solution, but in order to get the concentration to put in here, we have to take this and divide it by our 0.21 liters. So if we do that, we get 0.476 molar. Now, the acid that we're adding is 0.01 liters, or hydrochloric acid, and just in this problem it is also 0.5 molar. So we can see we're going to have 0.005 moles, and we're going to divide that by our liters, 21 liters. So we get a concentration of our acid 0.0238 molar. So that's our initial concentration. So here we have some of our base. We've added some extra acid, and that is going to change all these concentrations just a little bit, because all of our acid is going to be used up, which means we're going to use this up. We're going to make 0.0238 acid. So we are basically putting the acid H plus in. That's going to change our base, some of the base that's floating around in our buffer, and turn it into more of the acid. So we're going to change our ratio just a tad. So this will come out to be 0. So if I just do the math, I'm going to get 0.0 0.4522, and I'm going to keep way too many significant figures because I don't want to get too much rounding error, and I'll round off later. 4998 molar. Now, these numbers are numbers that I want to use to figure out what my concentration is. So I'm going to go on to another page where I have my standard numbers here. Here's my acid, and here's my conjugate base, and these two have been adjusted from the page before, and now we're back to our standard kind of a problem. Water, it's a liquid, so we're not going to worry about it, and we're starting off with 0 molar acid, and we'll do a standardized box. We see what's going to happen. This will be minus x, plus x, plus x, and this x is going to be nice and small, so we're going to be able to ignore it. So officially this is 0.4522 plus x, and officially this is 0.4998 minus x. Now notice in this box compared to the box I had before, my acid is on the right and my base is on the left, and now my acid is on the left and my base is on the right. So when I transferred my numbers, I had to be very careful to get the numbers in the right place. Now just substitute it back into my Ka expression. So I have x, because again we are assuming that x is very small, because it is, and our acid would be 0.4522. I'm sorry, my base is 0.4522, and my acid is 0.4998. And that equals 1.8 times 10 to the negative 5. And I'll leave you to do the algebra, but when we're done, we're going to find out that x equals 1.99 times 10 to the negative 5. So slightly different than 1.8 times 10 to the minus 5, just because my ratio, these two numbers, are no longer 1-to-1 as they were before. Now, if this is my x plus x, which is my H plus concentration, that's what the question is asking for. But, again, for your own information, if we took the negative log, that would give us the pH. And the pH in this case comes out to be slightly more acidic, 4.70, rather than the 4.74 we had before. And that's the end of this calculation.